to this. Cool.
Excellent.
Yeah. Oh, thanks, Mizey. I know Mizey's going to WTC, so that's why a lot of people, are on the way to WTC. I
Yeah,
think.
or some are already there.
Yeah,
Alex
summer.
Luke
Yeah,
Oh,
has
yeah,
been there for a
yeah,
while.
yeah. Alex,
so I might be able to break two two digits.
yeah. I think I've invited some people too, so I hope they come too. So,
All right.
yeah. So this is good.
Well, we
Um,
still got,
I mean, if you like, I can
12
always give it
minutes.
again.
Yeah. A lot of people
yeah.
can
Well, we
accumulate in waiting rooms in 2 minutes. Yeah. Oh,
yeah. I turned off the waiting room, so
okay.
hopefully we won't have any invaders. I've heard of that happening in Zoom.
Well, they say that Zoom bombing has fallen out of favor. The bad guys don't like it anymore. So anyway, it's no longer a fashionable crime area. Sort of
Well,
like
they
stealing laptops on planes. It was a big deal in the 60s and 70s, but it started not to make any sense. Yeah, after 9/11, it's like you really want to have a difficult life, steal a laptop on a plane. That'll do it for you. Yeah.
Yeah. Well, yeah. And Maisie, I hope your talk goes well, and we should get you to speak sometime also. And I know, it sounds like your talk would be great for this.
Yep.
Difficult to put all that information in 12 minutes, so I sort of, it was difficult to strategize, but I'm
Sure.
excited about the talk actually.
I bet
Yeah,
that'll
well,
be
we can give you like 55 minutes, so you can expand. Yeah, tell us everything. Tell us everything you didn't tell the World Transplant Congress. Yeah.
Well, I think we can actually, what I can do is start with the introduction, and then by then we should have enough people. And so I have a little few slides to talk about. So let me get started here.
Great.
Um, so yeah, so thank you all so much for coming today. Um, and so hope everyone in the Northern Hemisphere is having a nice summer. And thanks to everyone. If you have ideas for speakers, I think, sometime in September or after then, Maisie, just the same talk you're giving would be great, and other people too. And we have Dr. Wissett from the Mayo speaking in 2 weeks. And then we're going to talk about the Banff project on August the 28th. This is a grant that we've had with Kim and Parmjeet and some people at Kitware, and we're going to phase 2 renewal now, hopefully. So we'll probably give a report on that. And then on September the 4th, we'll talk about, digital pathology working group activities. We've had this survey ongoing for the community, and so we'll talk about that. We're probably going to expand it to other places. It's kind of a long-term survey, I think. It'll be interesting actually to see how it changes over time. And I think we're going to change it into that. We'll talk more about those things and other activities. And then on September the 18th, we have some collaborators of mine, Dr. Amit Kuskin and Aditi Kumar from Georgia Institute of Technology, and they're doing some multicolor staining, and especially on transplant and spatial omics. They have a lot of interesting approaches, and so that should be really great. So again, thank you all so much, and let me know if there are any speakers. Dr. Soles, Kim Soles mentioned that there's this ASN AI-powered kidney care network. So if you're a member of the ASN, join that and comment there. I need to actually do that myself. And because it looks they have some really great. I've read some of them actually. I'm getting them now, and it looks really great.
Cool.
And and then I think several of you will be going to the WTC in 2 days. Is when it officially starts. Some people actually, as Kim said, are already there. I saw Alex Lupe is already there, and his group probably are already there. But I think that it looks like a really great meeting. I actually have if we have time at the end, I have the PDF and I can show some of the special speakers. But I think now, though, I think we should go ahead and let Dr. Levinson and Dr. Richard Levinson he's at the University of California, Davis. He's been one of the best supporters of this group. And basically, these graphics are something that my PowerPoint brought up automatically. I have no idea how they came up, but he's great, and I really look forward to his talk. And he's like I say, he's been a great supporter of the group, and he's a visionary in the field. And I think you'll hear about that. So I don't want to take any more of his time, and I think I'll go ahead and turn it over to him.
Well, thank you so much. Um, it's really a pleasure being able to speak to this group, especially being someone with almost no renal expertise at all, because I'm coming from the technology side of things with the basic premise, which is that uh, things we are now finally in a position, I'll touch on this in my talk, that to do things a little bit different than we've done for the last 100 years. And I think that's really exciting. It's going to have implications, across everywhere. Um, and I just have to tell you about a frightening development I just read about that has nothing to do with this, but they I'm interested in AI, and I just read about a Chinese group that has developed a self-evolving AI tool that basically does everything, including creating the AI, evaluating it, testing it, coming up with new ideas, creating that one, evaluating, testing, and then it's just dramatically accelerated. So I was imagining what we could do with that in the world of sort of medical diagnostics. If we had AIs not just sort of following our lead, but actually leading us, it's going to be a very interesting world. And let me just share my screen if I can, and then see if I can do this with that. And oops, get rid of that.
That looks great. That looks great.
Okay, and um, wait a second. Why is that there? Uh, this is not what I wanted. Anyway, how's that look?
It looks good. Yeah. Looks
Okay. Is it
good.
full screen everything?
It's
Yeah.
full screen. Yeah, we do see your Mac, the bar at the top, but that's okay. I don't think it's a
Okay.
problem. I think it's fine.
Um, all right. Is that okay?
Yeah.
All right.
Thank you. Yeah.
So let me turn off the Roomba right behind me. We have 5 cats and a dog, and so we need to run the Roomba every day, or else we will be inundated. So anyway, I'm going to be talking, as I mentioned, new technologies for tissue diagnostics, and I'm going to touch upon the important question of the kidney, an important human organ. Well, let's find out. So anyway, what's shown there is the notion that we can enjoy life without glass. So you don't need a wine glass to enjoy wine, and you don't need a glass slide to enjoy pathology. Okay, so disclosures, I did found a couple of companies, one of which uh, their economic status is unknown at the moment, Histolix, but Muse Microscopy, as I'll show you at the end, has really begun to take off, I think, as a potential player in the actual real world of pathology. And so none of you need any of this, but I thought I would just stick in a couple of slides I use to tell people what pathology is. And of course, its origin in the modern era was from the autopsy. And actually, this isn't an autopsy. This is a anatomy lesson, but you get the idea. And then this, and then you can also look at tissues at sort of the semi-gross scale. This is a autopsy with sliced human brain, and really I point this out only to show that this is an oil painting, not a photograph, which I think is rather remarkable. So, and again, I point out to people that microscopy really is sort of key to medical diagnostics because we can see things even grossly when you look at it with the brain, but you can't tell what that white blob is unless you do microscopy. So, but the point is that the way we do microscopy now, and still even in this era of incredible evolution, is technically indistinguishable from what was going on in the late 1600s. And this is a picture of a real Leeuwenhoek microscope, and then in the middle and the bottom are pictures taken of a blood smear from a modern replica of that microscope. And you can see that the resolution is actually pretty darn good. Those are red blood cells. That's a white blood cell. And the point is it's not stained because they didn't stain much back in the day. And the real revolution in microscopy took place when actual stains were applied, and then the microscope was used to be diagnostic. And actually, it was amazingly late to get the microscope into the world of medicine. Most major players stuck with gross pathology, not with micropathology, until very late in the game. And it was the surgeons, not the anatomists, who actually made the evolution. The problem is it's still slow. So this is how we do microscopy at UC Davis. Biopsies at UC Davis on the left. And then, of course, as you know, there's lots and lots of processes that take place before we can slice the tissue to 5 microns thin and then stain. And that takes hours to days to weeks, depending on where you are in the world. If you're trying to be digital, you not only have to make the slide, but you also have to scan the slide. And all of this takes time and money. And the delays can be really problematic. And the reason I say that is I'm working, as you'll see at the end, I'm working in a global health capacity to try to move this kind of technology into areas like Africa, where there are substantial delays, months to never, in getting a diagnosis from tissue. So how can you skip the slide? Well, it turns out that there are now multiple different slide-free imaging technologies, some of which are really quite compelling and beginning to make their move. Of course, you know about confocal microscopy and multiphoton microscopy. There's OCT, which is at least can guide biopsies and things like that, but are getting towards the resolution needed. Structured illumination, which is a variant of 3D. Light sheet microscopy, which is really sort of making the move. One of the founding companies is just aligned with, I think it's Zeiss, to bring their stuff into the real world. And photoacoustic, which is a sort of novel hybrid method, which is proving to be remarkably and surprisingly interesting. But all of these typically require lasers or computers or fancy optical setups and high-end cameras and lots of money. And therefore, they're the real or generate huge amounts of data. So their practical significance in the real world remains to be seen, although I'm sure they will make an impact. And you can read all about it in one of my papers, which is referenced down there. So what we really need is something that's simple, so it doesn't look like that. Inexpensive, so it doesn't require gold. Pathologist friendly, and there's my picture of a friendly pathologist. And global. And so that's some of the things that we've been working on in our laboratory and with collaborators. And I should point out, and I'll say it a couple of times, that I'm very, very collaborative, because collaboration means that other people actually do the work, and I think that's a great situation. So we've developed, and I'm going to show you actually 3 different technologies that are strangely somewhat related. The first part is Muse, which is the first one out of our lab. And this was actually done generated by a combination of me and Stavros Dimos at Lawrence Livermore. And the basic premise is that you don't need to cut tissue thin as long as you just image a thin section. And one of the ways to be imaging thin is to illuminate it, cause excitation of fluorescent dyes with an ultraviolet LED. And the point about UV light is that unlike sort of visible light, which can actually, as you know, if you hold a laser pointer up to your finger, it can go all the way, it can go through centimeters of tissue. At 280 nanometers, it only goes in 10 or 20 microns at most. So that gives you a sectioning capability without physically cutting the tissue. And what I'm going to show you here, I don't think you'll be able to hear this because I can never get that to work. But this is my, I'll read it. Seen things you people wouldn't believe. So that's what I'm going to show you is I think some things that are really, really cool. So, and this is demonstrating the difference between exciting tissue at visible light, 405 nanometer, which is blue. And this is lamb kidney, and it's just been stained with eosin, and it's a relatively low power. But you can see that there's a lot of structure there. There are tubules and collecting ducts, and it's sort of a mess because this actually came from a butcher shop. But that's what you see when you excite the eosin at 405. Now, the same exact, nothing was changed except the excitation light in the next slide. That's exactly the same region. And that's what happens when you excite at UV. You only go to the surface, and so anything that's on the surface is high resolution. Anything below that is not even present in the image. And so that's what we're going to be using to look at thick pieces. I'll show you different things, but a lot of kidney with UV excitation. And please, please stop me if you have any questions along the way. So here's an example, and the resolution is very similar to standard H&E, and so this is just a side-by-side showing ductal hyperplasia of breasts on the left, standard H&E, on the right, similar tissues imaged with Muse. And the point is that it looks funny, the colors are all weird, but it's easy to actually convert that. I think I have one or two examples. So it looks just like H&E, indistinguishable from H&E, just using a color mapping. But you may not want a color map because there's a lot of rich colors here, all acquired in a single snapshot. So we're not using multispectral, we're not taking multiple images at different wavelengths. This is just a color camera, and this is what the color camera sees. And this is kidney. There are tubules and whatnot up at the top. There's a relatively large vessel down there, which I think I'll zoom in the next slide. But you can see the muscle layers, the internal and external elastic laminae, and then what's really nice when you're dealing with 3D tissue, and I'll show you some more, is that you don't just look at 5 microns, you can look down into 3D structures. I call this 2.5D. And so you can actually see the endothelium as it's going down into space there. And here's a close-up of that. And this was stained with 20 seconds of a single dye solution, a combination of Herxt for the nuclei and rhodamine for everything else. And what you're seeing is also autofluorescence. So the elastic laminae and the collagen, basically the collagen wasn't really stained, but it's autofluorescing in blue. So you can see exactly where the collagen is, where the elastin is, where the muscle is, just with a single snapshot. Here's another kidney.
Very interesting source because a lot of people in India think that
Say it again. Okay. So again, blue collagen, yellow elastin, and then you can see the structures of the kidney more or less. not just deep, but also longitudinally, you can see elongated structure. I'll show you one or two vessels from the kidney, but this is vessels from the surface of a cut surface of fresh breast. And it's a lovely picture of a blood vessel. Up at the top, I think you can see some nerves. And of course, the fat is still fat. It hasn't been removed by all the xylene. And so if you wanted to do lipidomics, it's still there. You're welcome to. Also, collagen has 3D structures, which we don't appreciate when we only look at thin slices. So this is a mast cell tumor. On the left is conventional histology. I'm not sure. I can't remember the dye, but the collagen is showing up pink. That may be H&E. And on the right is one of our images of a mast cell tumor of a dog. And for some reason, I forget what, I think that's acridine orange, maybe. The mast cells are yellow, but the collagen, which was not specifically stained, but it's just autofluorescing blue, you can now see is actually in fibrillar structures. And although that's not diagnostic of anything now because we don't really have the correlates between appearance and outcome, you can certainly get a better sense of what the tissue actually looks like. Single shot, no computing. It's just what the camera sees. You can also look at surfaces that are very hard to see when you're doing transections with on a microtome. This is the inside of a colon, and that's the lumen, and this is the actual surface that you see. This is basically the exact analogy of what people see on endoscopy. You're looking at the colonic surface. Each one of those sort of round green things is a crypt. And you can see the mucus secreting cells at the top, the little sort of, you can see my mouse. And let's see. I want to do annotate. Anyway, and then also things that are very, very hard to see. This is the endocardium, which is an extremely thin cellular layer on the inside of the heart. And normally when you looking at a heart slice, you can see maybe one or two endocardial cells on the surface, and you don't get a sense of how they actually lie. So all of these little white things up here are the nuclei of an endocardial sheet. Down here are the actual muscle cells in the heart. And you can't see this unless you do en face microscopy, which is very, very easy with Muse and the other stuff that I'll show you. Now this is kidney. These are proteinaceous debris in the tubules, standard H&E. And then again, a little bit of 3D. You can see the things in there in the tubules, and then actually popping out, and you can see that they really are, toothpaste, little bits of toothpaste in the tubes. Also, you get a better sense of the structure of things. I'm just showing you this. This is a Muse image of kidney, obviously. And now you can really sense that the glomerulus is a sphere sitting in the Bowman's capsule. And actually here where you have a single shot without extended depth of field, the blur gives you a little bit of sense of 3D. Here's a nice blood vessel with very thick walls. Here's another blood vessel with thick walls, and you can also see the elastic lamina. And collagen here in the blue. And you can see the two different kinds of convoluted tubules. They actually stain different colors, yellow and bluish. So it's nice you can see that. Here's another example. And what I wanted to show you is really what you lose when you look in bright field H&E. So I'm gonna simulate bright field by just taking this image and inverting it, so that now we can clearly see these tubes they're tubular, they have structures, they're 3D. This is essentially a 2D slice through it, but we're getting clues as to how they look in real life. Now, if we just invert the image, you can still, which is, more or less, I could convert the colors fully to H&E, where the nuclei would be blue and the tubules would be reddish. But the point is, if you look now at the tubules, the data is exactly the same. The shading is the same. It's just inverted. But we now, because of the way our brains work, we've completely lost the clues as to the 3D structure. See, they are holes, right? They're going down into space. Here they're just sort of white areas. And so I think this is, again, I don't think it has any real diagnostic implications, but it is an indication that the tools we use to see things are limited. And this is I show this only because it's not safe for work, but now you can really see down into these structures as physical structures with shapes and implications. And I think especially for prostate, when we're looking at Gleason grades and how the tumor is kind of 3D in structure, I'm hoping that we can do better 3D or Gleason scoring with this extra little bit of surface information than it's just a thin slide. This is just a pretty picture, more kidney, vessel in the renal medulla. And here are the endothelial cells down here. Here's the muscular wall, which is open but folding over on itself. And this has zero utility, except I just love it as a sort of as a slice of life where we can actually see what these structures look like. Again, really simple, just a cut with a knife, image in 100 milliseconds, stain for 20 seconds, image in 100 milliseconds, and you get this. As I said, we can take those funny looking colors and convert them into H&E. This was an old tool that we used, but just to show you that the colors can be generated and be very convincing. And just to sort of drive the point home again, here's a nice tubule with a hole. If you look over here, it's got a white space, but you've lost that 3D clues. All right, so that's all Muse. And I don't know if you have any questions specifically about that technology. I can then switch to Phibi, which does exactly the same thing, but surprisingly doesn't use UV. It uses the blue light that I was making fun of before. Instead of fluorescent dyes, it uses absorbent dyes, in fact, specifically hematoxin and eosin. So if you recall my last optical diagram image, this looks very similar, except all we've really done is switch to a dichroic and epi excitation with a 405 nanometer LED, blue LED, $5. And the point here is that the tissue again is thick. It's just compressed against now a glass, not UV transparent surface, and it has been stained for a minute or less in H&E. Just the surface is stained. And the way this thing works is not cause fluorescence of the stains. It actually, the blue light comes in, goes through the top of the tissue, down into the deep tissue. The tissue actually has to be deep. By deep, I mean thicker than 60 microns, to actually generate autofluorescence, which is this blue haze here I'm showing. That blue haze, and it's multicolor haze, I mean, it's basically broadband haze, then comes back, some of it comes back through the surface, collected by the light, by the objective, and hits the color camera. And in fact, we for years had a box that would do simultaneous or sequential Muse and Phibi with everything the same except just flipping the excitation source. And there is a nice picture of a breast lobule. And the point here is I didn't even have to invert it. That's what the camera sees. There's no computation except maybe a little photoshopping to boost the brightness and color and contrast and that sort of thing, but really no fancy math. And so that's what I'm going to show you now with some kidney as well. How does it work? It does require the absorbent stain. So this is just the autofluorescence if you don't stain the tissue. Then if you stain it with hematoxin, you then see some contrast, absorbent contrast. And then if you add the eosin, it then begins to look more and more like standard H&E. And the images are pretty convincing. This is a normal breast lobule, 20x lens, thick tissue, okay, not a thin section. This is, I don't know, a millimeter thick. And that's what we see. And And we can also image the face of paraffin blocks. So you don't, if you say, oh, I wish I could, I need to go back and look at a paraffin block of something or other, you don't actually have to make a slide. You can just quickly deparaffinize the surface of the block, stain it with H&E, and image it. And this is the surface of a paraffin block of squamous cell carcinoma, oral squamous carcinoma. The other interesting thing about FIBI, as with Muse, is that you see more color. Again, this is only H&E stain. This is the same structure, first imaged with FIBI, and then we made a slide from the same region. And so this is the exact same vessel, and this is the vessel wall on H&E, and you can see it's there with blood in the middle. But the wall is basically there's sort of no interesting signals in the wall. Same vessel, same wall, but now you can see 5 or 6 layers depending on how much coffee I've had. There's just more information there. What is this structure here, just below the surface of the outside of the vessel? Don't know. There's a world of knowledge to be gained by looking with this extra contrast and correlating with disease. Again, because the tissue is thick, not thin, you can see structures, longitudinal structures with much greater structural integrity. So same cat bowel. We have a vet school at UC Davis. This is the inside. It's sort of flipped because of the way the tissue shrank. These are the villi. And if I just showed you this, you would tell me that villi are little oval things that float in space. And of course, that's not what villi are in the small bowel. This is what villi look like. And so this is actually, we imaged this in the face of the paraffin block. The villi are intact. Also, we don't see all of the artifacts of H&E, all of the tissue cracks, because the muscle here is perfectly fine. And this is overexposed, but this is the sort of the collagenous area. So now this is just a picture of a mouse kidney that we took with FIBI recently. And I point out here only to show you that we can see the things in continuity that are hard to see on standard slides. So here's a nice vessel going all the way through. You can see little sub-vessels coming off of it. You can see the tubules and whatnot. But speaking of vessels, and I think this is going to be very interesting for especially for cancer research, to look at the structure of the microvasculature around tumors. This is now FIBI and H&E, same structure. This is a little nodule of breast cancer. H&E, here it is with some inflammatory cells. And here's a close-up of this region down here. So this is obviously the same region, but from a thick piece of tissue before it's been sliced into a slide. And if we look down here, this vessel here is the same as this vessel here. This is FIBI, this is H&E, there's the yellow star, so same. Now, if you look here, you can now see capillaries that are doing whatever capillaries do, a nice little structure. We can evaluate them, we can appreciate them, we can quantitate them. If you look over here, they're here, the capillaries are here, but we don't see them because we just see a little tiny circular sort of sections through wherever the knife caught these vessels in as they're moving along. And so we can't really say anything about the capillary structure from here. So I'm very excited about this. We've actually doing some serious math on the vessels that we're seeing with breast and prostate cancer, and we'll see if we see anything. So here's just a couple more pictures of kidney with FIBI. And again, I'm pointing out to you just a couple of things, a little bit hard to see, I think. But here's a blood vessel, a little bit overexposed, but you can see the elastic laminae, and then you can see the vessel coming down here. This is the vessel going down and actually feeding this glomerulus. So you can actually see how vessels and gloms and other structures interrelate. Here's another example, also pig kidney, sort of a bigger vessel, and you can see down here, here's the vessel coming down more or less intact to feed this glomerulus. So that's really all I have to say about that technology, and I'm going to finish with another technology soon. But I did want to say that first of all, as I mentioned, This is beginning to hit the real world. Muse Microscopy is a company that I founded and then had a falling out with the previous management group and had nothing to do with, and then behind my back they sort of pulled themselves together and actually have made a major move into the field. Here they were platinum sponsor at USCAP meeting earlier this year. And they've actually built some prototypes. So this thing down here is a box that will actually do slide imaging in seconds that I've shown you. And we've also taken the same or the Phoebe technology. This is me as the Phoebe technology to see if we can do something for breast cancer diagnostics in Ghana. And so we have a grant to do that with my collaborators, Eric Seibel and Beatrice Weafe, who is a founder, a breast surgeon in Ghana. And as you can see, breast cancer is the #1 cause of cancer in this whole region, including Ghana. And there's a core imaged. And we've actually, one of my collaborators, Mark Fowler at University of Washington. So this is Beatrice. And here's the box that we sent. It's in Ghana now, and they're actually taking images of patient specimens with great excitement. So last part of the talk is about Duet, which I think has really got some serious implications for renal diagnostics. So this is a new way of imaging conventional H&E slides that all of you have already. And this is just a way of getting more information directly from the slides and potentially avoiding the need to do special stains. And what it is simply, it really is simple, just image the slide in bright field and then switch to long pass fluorescence. And if you image in long pass fluorescence, basically the tissue, which is stained with H&E but has its own autofluorescence, creates an image that looks mostly green, but it has a lot of color information in it. And then you can combine the two to see wonderful stuff. So this is sort of random cancer with collagen around it. And then my colleague, this is developed by Farzad Faradouni, who I think will be presenting this in greater detail to the group later. But if you use spectral phaser analysis, which is just underneath the hood, just a way of visualizing the distribution of color information in this case, it's sort of each little dot here is a pixel from over here, and they cluster in color. And then if you look at this cluster, it's the red cells. This cluster, it's sort of everything, and this cluster down here turns out to be just collagen. And so here you can see lots of pink on pink. This is I challenge people, I say, what's what? But this is the muscle, this is the nerve, and this is tendon. And of all these three things, only tendon is mostly collagen. And here's a duet image of this structure. In other words, if we just add the information from the fluorescent channel, there's the collagen. And sometimes you really cannot see the collagen in standard H&E. Standard bright field. So here's a bit of liver in bright field. And then if we image it in fluorescence, bingo, the collagen now just shows up, as I've been showing you before, with blue autofluorescence in this particular case. And then you can obviously pull out the collagen as a separate channel. But honestly, if you look, yes, it's not really liverish, but I really can't see the collagen fibers here at all. Or here, looking at all these blue channels, blue signifiers. And so it's just remarkably simple, stupidly simple, but it's right, the information is right there on your slides right now. But interestingly, it also, because it's a color image, it gives you more information than what you would simply get from a collagen stain. So this is liver with a bunch of collagen deposition. And here's the trichrome stain of this region, and you can see there's collagen, and it's all blue. But if you look at the duet image of exactly the same region, you can now see, and I have zero understanding of what it means yet, this collagen up here is blue, and this collagen down here is kind of a dirty green. I don't know if one was deposited early before the other, if it's got other, sort of molecular features, but it's different. And again, this is the beginning of a way of looking at kidney with a novel contrast. Here's kidney. Again, where's the collagen? I mean, you can sort of see the stuff that isn't tubules, but here's the collagen signal, and it's also sensitive to type 3 and type 4. It basically all the kinds of collagens. So you actually see the collagen in the glom as well as outside the glom, but trichrome or uh, picrocerius red doesn't stain all of the collagens, which is potentially specific, but it's also you're losing some information. Is it really showing us collagen? And the answer is it seems to be. So one of the ways of seeing collagen is an optical technique called second harmonic generation, and so we can actually image this piece of non-liver with NASH, non-alcoholic steatohepatitis, which is characterized by sometimes fibrillar deposition of collagen in certain regions. And here you can see that's sort of a mess, but you can't really say, just looking at this, oh, that's collagen. Here is the duet signal saying, I find collagen here, and these little things down here, which are completely invisible on the bright field. And then we can take this blue and look at it as sort of yellow against a black background and compare that to the SHG of exactly the same region. And lo and behold, these little tiny features are showing up with this very fancy optical technique. But it's also showing up here. And so this gives us some nice confirmation that we're not just fooling ourselves. But you can also use Duet to simulate the different stains. So here is actual trichrome, actual PAS, and then on the left is the H&E, and then our computation of collagen down there just from the H&E stain, and then our computation of elastin, again, just from the Duet image. So that's potentially interesting. And again, as I showed you with Muse, there's more colors, more information than you can see with standard bright field. So this is a vessel, and then if we just switch to fluorescence and look at this channel and boost the contrast, you can actually see all of the layers now of this vessel wall, including something that is completely unexpected, which is that the elastin comes in different colors. It comes in yellow and blue, and there's actually no clue whatsoever in the bright field. And you can see all this collagen, the nice fibrillar structure out here. So potentially exciting. And again, this is some form of breast cancer, I believe. I've forgotten. This is the bright field, and let's just look at this again under long pass fluorescence. Didn't do anything except switch how the microscope was capturing. Look at all of the colors in that identical, that is exactly the same field of view. Same lens, same camera, just switching to fluorescence. And you can see now there's a layer of this layer here, which is sort of this whitish area. And then there's green here. I don't even know what it is. And then the collagen, sort of standard collagen, is all this yellow stuff out here. You can actually see the fibrillar structure of the collagen much better, easier to appreciate than you can on bright field. Although you can ramp that up by changing where the condenser is and that sort of thing. What does this all mean? Again, I have no idea, but for smart people like you, it's a whole new world to explore. So my conclusions are, I've reached the end. Novel microscopy techniques might be useful for addressing clinical histology-related renal questions and their global health implications, as I showed you with that Ghana thing. 2, I am very happy to collaborate. And 3, I want to reiterate that the kidney is an important human organ, and that's validated by our dog, Maggie, right there. And that's actually not something from one of the space telescopes. That's breast. And this is actually, these are not current people in the lab, but I just wanted to point out, you'll be hearing, I think, from Farzad soon. But just to point out that this didn't happen by Neil, and many, many people contributed to this. Thank you for your attention. This is from a tree near my house, and this is our cat Toby.
Well, that was really great. I mean, I love the way you present, and you know, I know everyone has a lot of questions, but actually, I had one to start off, and I think I've asked this to you before, and also I asked Farzad before, but the ones that you have to stain, d does that still preserve the nucleic acids?
Yes, so
Um,
you're talking about the for
like yeah,
mutants.
yeah.
Amphibian. Yes, we've done that stuff. We can take it, and the nucleic acids are fine. Immunohistochemistry is fine. Standard H&E after, as I've sort of shown you, after Muse or Phoebe is fine. So it doesn't, and the actual process of taking a Muse or Phoebe image is non-destructive. So unlike frozen sections, you don't lose any tissue. So it's all there for whatever you want to do downstream.
Cool.
Right, awesome.
Lynn has a question.
Yeah, I have a question. Thanks a lot. That was so interesting and interesting to hear all these different techniques that you're developing. I have a question about both your I guess Muse and your duet technology. So in the kidney, a lot of what we're interested in looking at in medical kidney disease is immune complex deposits and glomeruli. And in the transplant, C4D deposition and also the nature of the inflammatory infiltrates. And is there any way that you had talked about different colors and showing collagen and blood vessels and everything, but is there a way to reliably detect, for example, immune complex deposits in glomeruli or distinguish different types of inflammatory infiltrates? That's really what a lot of what we have been interested. I mean, I'm sure there's more to look at in the kidney and medical kidney biopsies, but at least those kinds of things are you able
Sure.
to? And especially thinking of, um, you know, lower resource areas where pathology labs maybe don't have access to immunofluorescence labs, for example. Is there any possibility of using your technology for something like that?
You just signed yourself up for a collaboration. There are sort of several answers to this. First, we're working with novel, so we're trying to develop real-time immunofluorescence that would work actually on that same specimen with that same instrument without even changing the instrument. So and so we actually, so that involves not only getting stains that, immunobinding to work, but also stains that are very, very bright and detectable. And we're actually working on that. There are novel fluorescent dyes or compounds that are 1,000 times brighter than quantum dots and don't photo bleach and can be complex to immunostains. And show up very nicely just in our Phoebe box. Had 405 nanometer excitation, same stupid color camera, So theoretically, and we're still working on that. So the notion is it's theoretically possible to do immunostains directly on this thick tissue in real time. The sort of fallback is, well, no, you can't do that, but at least you've seen the structures that you're interested in, and you haven't destroyed anything with doing Phoebe. So then you can say, I'm going to take this specimen and I'm going to do immunostains secondarily, and at least you can still do that. And the third pie in the sky is that AI, morphologically based AI tools can shed enough light on what's going on. That immunostains aren't needed anymore. And a lot of people are doing that work in lots of fields. And I don't know what's going on specifically in kidney, but it's a thing. And you can use the Phoebe images as input into the morphology-based AI tools. So the short answer
I
is,
guess a similar response to the nature of the inflammatory infiltrate and location of the inflammation.
oh yeah, I mean, look, you can easily detect inflammation. You can usually detect, we can see lymphocytes. I don't think we can necessarily tell the difference between B cells and T cells, but we can see polys and eosinophils and lymphocytes, and we can certainly identify where those things are. So that's at least a little bit down the road of what you're asking for. Stunned silence.
Yeah,
If no one
Monty
has
has a
a
question.
question, I have one. So if I missed the point in the beginning of your presentation, does this technology works only on the tissue, not in the actual slides that have been completed and cover slipped?
Sorry, I talked about three different technologies. There's Muse, Phoebe, and Duet. Muse and Phoebe are thick tissue. Typically biopsies, I mean, I don't want to get into the in vivo imaging world, though a lot of people are doing that, but a chunk of tissue, you take it out with a needle, you take it out with a biopsy forceps or something. That's thick tissue, that's Muse or Phoebe. Looking at the H&E stained slides that you already have, that's Duet. Does that answer your question?
Yeah. So that's what I was thinking. Like, say that we have thousands of slides, and you cannot really go back to the source tissue, right? So how can you theoretically apply this new technology? So that's Duet, right?
That's Duet. You
And
just look, you just have, and you can do it on your regular microscope as long as you have a sort of regular fluorescent microscope. All you do is switch the filters out so that it's instead of bandpass, which is typically what people have, they have a DAPI and a rhotamine and a fluorescent setting where they're just looking at, excite here and just image this little bit of color region there. What we do is we excite here, but then we collect all of the color information. So you just have to change your emission filter to a long pass, and then you can do Duet right now on your scopes.
That's great.
Ozzy,
Monty,
yes,
would
question?
Thank you very much. That was an amazing talk. Makes you want to put everything under those microscopes and see what you come up with. A question I have is, what is the output in terms of file size? For example, for a core biopsy or maybe a typical wedge resection.
Just the same as you would get, actually, I mean, we can image a whole slide at 20x, and we can output it in standard sort of SVS format or TIFF format, or pyramidal TIFF, which is like an SVS. So it's no different than any other digital pathology information. And of course, if you're just looking at individual fields, they're tiny. It's a few megabytes.
And have you tried rotating the cores and so that you can cover the whole depth of the tissue and see if you can reconstruct a 3D image?
We can certainly look at the top and the bottom. That's easy. What I want to do actually is to do sort of bread loafing tissue. This is, people often mention this, especially with prostate, because sometimes the tumor isn't on the surface. And I guess in kidney you might be missing the gloms that are inside but not on the surface. So my theory, which we haven't quite done in practice yet, is to take sort of little, just imagine the core as a loaf of bread and just make slices every millimeter, let's say, and then flip them so that you're looking now through the entire thickness of the core, but as a bunch of little little things that are all lined up. And that should be easy to do, especially if you sort of put the core in some agarose to hold it and then cut it and then flip it. So it shouldn't take long. And then that way you would get basically a complete image of the core in its 3D. You'd be sampling in 3D the whole core. Obviously, you wouldn't be getting a total 3D volume, but that's really not worth the effort. But I think, and again, I was meaning to yell at my people in the lab yesterday to do it, but they've got lots of other stuff to do. But it's something that I think would solve that problem, and it could be easily done with the right little tool, a sort of slicer, and then just flip, 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 and you're good.
And my last question is, how expensive are these microscopes?
Well, the Muse microscope was implemented on a cell phone with self-contained. In other words, it's all powered from the cell phone with $20 of printed optics that you just go right over the thing. So it's theoretically extremely inexpensive. The stuff that I've been showing is expensive, but only because we're using to do the scanning, we're using sort of high precision stages. But if you want to skip the high precision stages and just move things around manually, it can be, a few $100s. I mean, in other words, cheap.
Thank you.
So you're all going to switch to Duet now?
Tempting.
All right. Thank you.
What about, have you looked at like amyloid or
Yes, it shows up. It does show up as a different color. And the other thing is that a lot of deposits are all visible and they all have different colors. And so again, I want to collaborate, but I think there's a world to be explored here.
Yeah, thanks, Brad. I was also thinking about amyloid when I was looking at those pictures of collagen, and I forgot to ask about it. But
Yeah.
one thing about amyloid is that it can be so focal, and really minimal. And I'm wondering do you know how sensitive that I don't know any of your techniques might be for detecting it. Like especially if you're able to see these different colors within collagen, you can imagine amyloid might show up. But again,
Right.
amyloid can be really minimal. It's not like a big blob there necessarily.
Right. Well, I don't want to make any promises. I think it's worth looking at. Let's put it that way.
Cool.
Another thing I thought of is something Lynn's an expert on is these oxalate crystals and other things. So the thing about some crystals like urate, they dissolve with our standard processing. So if you could image before and get the things that go in lipid also and fat in the liver and stuff like that. So have you looked at like crystals, like things that are
No, have not. Um, you know, we just grab a mouse from somewhere or go after sort of just one particular thing like breast cancer, but we haven't really explored all of the wonderful things. Now, we have been working with, and mostly Farzad, with Pinaki and Duet, but I don't think they've been exploring all of the questions that you've been asking. So there's a whole world of new science, new grants, new money for you all to be looked at.
a lot? I'm definitely going to think about it a lot.
And you can send us, I mean, it's no big deal to take those images, but you can send us some slides of interest and we can take a look as well.
Okay. Yeah. Yeah. Awesome. Well, thank you so much. Are
Pleasure.
there any other questions? I'm sure we'll have you again in the future. And also, we had Farzad in the past, but I know he's done a lot of work in the kidney since then. So we might have him, like you said,
But
again.
just the interesting thing, which I didn't touch on, is that he's been doing work with Pinaki on duet enhanced AI analysis.
Yeah.
Mhm.
Yeah.
So
Yeah.
that's again, you have twice as much information going into the same AI tools. You should be able to do twice as well, right?
Yeah. Wow. That's awesome. Well, and I think that I had mentioned that Banff aid, that project that's been ongoing, I think they're now trying to like some sort of like merge with Panaki's group,
Mhm.
their efforts. So I think that might be part of the NIH proposal, maybe. So I'm hoping that works out.
Awesome. All right.
Great.
Okay. Well, thanks a lot. You take care. Thank you all so
All
much,
right.
and
Are we done here?
hope everybody has a good time at WTC if you're able to
All
go.
right.
Thanks
Bye.
again for presenting. I really appreciate it.
Bye.
Bye.